Hi everyone, hope you're all well. So we're going through the Practical Electronics for Inventors book by Paul Schurz, and the purpose of this is so that I can get up to scratch with AC electronics. So in the last video, we went through phase. So I did a bit of phase, and I'm just going to continue finish off phase, and then move on to AC and resistors and RMS voltage and current. So let's get straight into it. So another special case occurs in Figure 2.85D, which is here, where waveforms A and B, so these two waveforms, are 180 degrees out of phase. Here it doesn't matter which waveform is considered the leading or lagging. Doesn't matter. Okay. Waveform B is always positive. B is positive when A is negative. And vice versa. If you combine these two equal voltages or current waveforms together within the same circuit, they completely cancel each other out. Interesting, yeah, because the average will just be 0. Ah, it's interesting, isn't it? Okay, so if you've got voltage here, there you've got let me draw a full one. You got voltage A, and then you got voltage B. Is so wait, so where A crosses the line, then B starts where A ends, like this basically. Okay, best thing to do is copy this, duplicate it, or even go back a bit. That. Yeah. All right, so now I this. Okay, so A and B. So B, A. So A and B are 180 degrees out of phase. The reason why I'm taking notes is because I'm gonna excuse me. The reason I'm taking notes is because I'm gonna go back through these notes and turn my notes into flashcards and questions for me to practice and start to learn. So the reason I don't want to do that through a book is because the book's just got loads and loads of information, and there's only certain bits of information that I either feel like I need to know or want to know, etc. So yeah. Okay, so if A plus B, then they completely cancel each other out. So for example, one question I'll write there is, what happens when two waveforms that are 180 degrees out of phase are added together? Okay, so moving on to now AC, resistors, RMS, and current. Cool. The alternating voltages applied across a resistor will result in an alternating current through the resistor that is in phase with the voltage. That is in phase with voltage. Figure 2.86. Where's 2.86? Here. Current that is in phase with the voltage. Okay, meaning this phase is the position, right? So that the current is going to be in this exact same position. All right, so it's going to look exact. It's going to be, yeah, got it. Okay, so how can I turn this into notes? So so AC voltage across a resistor equals AC current for alternating current, because I just want to make sure I get the point that it's alternating current. So meaning current goes backwards and forwards through the resistor. Alternating current through the resistor. Through the resistor. This current is in phase with the voltage. Okay, this current is in phase with the voltage. I kind of, so if two waveforms are in phase, but you can have a current waveform and a voltage waveform, right? So let's say that this is the voltage waveform. Let's do it a bit differently. Let's do this, the voltage waveform. Then this could be the current, for example, right? And where basically it follows. So it's exactly the same. Not even that it's following, it's exactly the same, just of different, obviously, magnitudes on the scale, right? That's what that so these are in phase, right? I'm pretty sure that's what that means, that they have the same peak. The peaks occur at the same time. I think that's what that means. I mean, there's not really much clarification, but okay, let's do this. What does it mean that two waveforms are in phase? Have a phase difference. Two waveforms, same frequency, that are perfectly aligned, have a phase difference of 0, are said to be in phase. Okay. So the current is in phase with the voltage. Alright, so in phase then means perfectly aligned. Perfectly aligned. That's an important point for me. Okay. So, given the AC voltage and resistance, you can apply Ohm's law and find the AC current. Okay. Ohm's law. So, AC current is equal to AC voltage divided by resistance. For example, a sinusoidal waveform generated by a function generator. Okay, so sine wave can be mathematically described by, what's the T? I don't get that. What's with the T? VT. Okay, so basically that VT means the voltage going along the whole time. This whole bit here. So like this whole, because obviously it's varying values of voltage, but all those varying values of voltage are, and that's what that means. Let's just write VT is means all varying values. Tell me if I'm wrong. If you know I'm wrong. VT means all varying values across time. You know, like here, 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 and here. Okay. So sine wave. A sine wave can be described, is described. Let's put can be. Stick to what they put. Can be described as the voltage time is equal to the voltage peak times sine of 2 pi. Why is it 2 pi again? 2 pi being 360, right? So being, I don't get it. Okay, I think I took that. I think I took notes on this previously. Okay, here, so unit circle. The 1 radian. Okay, so 2 pi is 180 degrees, right? Yeah, I think I'm pretty sure I took like actual solid notes on this here. Okay, so no, 1 radian is 180 degrees. So 2 pi radians here. So this is just saying 2 pi. 2 pi in relation to here is what? Why is it 2 pi? I think this, okay, I think it's just saying basically 2 pi radians, right? I think that's what. Okay, so 2 pi representing, bloody, I'm yawning a lot. 2 pi representing the one whole cycle, I believe. And then you multiply that by the frequency because that is obviously how many cycles per second. And then you times that by the time of how long the signal went on for, right? If you put voltage through a circuit for 60 seconds, right? Then you would have the voltage peak, which is 10 volts. Then times that by the sine of 2 pi times, I don't know if you put 10 volts of, I don't know why you'd put 10 volts of AC, but fine. You put 10 volts of AC. So is it 50 hertz or 60 hertz in the UK? I think it's 50 hertz. So 50 hertz. And then times that by 60. And then that you'd be able to draw the or the whole waveform. I believe that I don't know if that's right. I'm reaching here. Okay, so anyways, let's just go with what they said. Where VP is the peak amplitude of the sine voltage waveform. F is the frequency and T is the time. Using Ohm's law and the power law, you get the following. What? Why? I don't get it. Where are you using Ohm's law? And why have you just introduced a bunch of... So I assume you're swapping voltage for IR. Like, just explain what you're doing. Like, it would have taken an extra paragraph. That's it. Oh, man. I bet some dumb editor took it out. He's like, no one needs to know this. I do. So we're saying that current throughout time is equal to voltage divided by resistance. Okay. So what does that have to do with the equation you mentioned before? Okay, you're just saying separately that I is equal to V divided by R, right? And then you're saying, well, okay, V is actually the voltage peak times sine 2 pi times frequency times time. But then shouldn't it all be divided by R? I'm not sure I'm not sure I understand why it's just the voltage peak divided by R. Or is that yeah, I don't know. I don't get that, but that's fine. Okay, so at a certain point I need to learn a bit more to just be more accepting of what the book's telling me. So defined current through, are we still talking about the resistor? So defined current I is equal to V divided by R. Substitute. I want to say substitute in VP, substitute VP, substitute V for this equation. So I is equal to VP over R sine 2 pi times F times T. I don't understand why it's only VP over R. Okay. A good way to know this actually would be to basically, if you do this on a calculator, do they both work out to be the same, whether it's VP over R or all of this over R? Does it work out to be the same? Because if it works out to be the same, then I'm writing my brain for nothing. Okay, so I have to make some assumptions now from some numbers. So V is equal to okay, VP is equal to 2. R is equal to 2 as well. Let's make R equal to 3. And F is equal to what's frequency 50, right? And T is equal to 3 seconds. Anything else I need? No. Okay. So we're saying 2 divided by 3, right? Times sine. Am I in radians or degrees? I'm in degrees. The sine. Don't know what I need to be in. Do I need to be in radians or degrees or radians? Don't know. So 2 pi. It must be radians. 2 pi times F. So F is 50, obviously. Times time, which is 3 seconds. What is equal to 0? What did I do wrong? Not sure what I did wrong there. The sine. This is saying it's equal to 0. Why? Now it's not. I don't get that either. Okay, so answer. Okay, so anyways, this is equal to 0.456. Let's try the other way now. Let's try all of it divided by R. So you've got 2 times sine of 2 pi times 50 times 3. Okay. Then we're dividing all of that by 3. 0 point minus, right? Did I miss out the minus before? Because they're almost the same. Ah, I've got to go back and do the previous one, don't I? Can I go back? Okay. Crap. Hey, it was minus. Oh, wait, no, wait. Huh? I'm confused. Okay, yeah, no, because I'm sorry, I just whacked the mic. So I divided V by R first. Okay. So yeah, I must have missed that out. So they're basically the same. No, they're exactly the same. Okay, so whatever. So in case you didn't get what I was doing there, basically, I was trying to see. I wanted to know why, if I'm substituting in this equation, why am I not dividing the whole thing by R like this? Wait, I'll do it here. Why am I not doing that? That's what I wanted to know. But it turns out they're exactly the same equation, which mathematically I don't get that. I don't get why they're the same. But yeah, fine. I accept it. But anyways, oh crap. Oh wait, no. I didn't need the actual figures. But so that's how you would work out then. So okay, so let's go through. So that's how you would work out the current or the peak. You would work out, okay, so using this, you would work out the peak current. The peak current. The current at the voltage peak of the waveform. Or the current at the peak of the waveform. That's how you do that, right? I think this is what this would do. I keep writing down what I think, and it's not really established that it's true, and that can be a problem in the future, but it is what it is. It's fine. You know, hopefully it gives me more opportunity when I go through my notes to hopefully try and correct some of my assumptions. So this is the current flowing at peak of waveform. I think in brackets. Okay. Alright, so I'm fine with how you get Ohm's law from that. That's cool. If you graph both voltage T and IT together, as shown 2.86. 2.86. Voltage T and IT. I don't see how you grow. You've growth. Okay. So this is VT, the whole thing. The current. Okay. But how are you saying? How would it be possible to graph these? Oh, because there's no values here. Is that what you're saying? You're just saying stick it on a graph, but don't use any actual values. This could be, 150 volts or 10 volts or 2 volts. So if you graph both of these, I wonder how you would graph that. I don't even know how I would go about doing that. You notice that the current and the voltage are in phase with each other. You have to take your word for that, because I don't know how I would graph these. Okay, so like the first 50% of the waveform is exactly the same phase as the first 50 is like, yeah, whatever. Basically, they cross the zero mark at the same point. They hit their peaks at the same point, so they're in phase. Okay. So as the voltage increases in one direction, the current also increases in the same direction. Yep. Thus, when an AC source is connected to a purely resistive load, okay, the current and voltage and phase. Alright, so when AC source is connected to purely resistive load, I and V are in phase. This means, to remind myself, they have same peaks, cross zeros, 0, etc. Okay. If the load isn't purely resistive, i.e. has some capacitance and inductance, it's a whole different story. Oh man. Yeah, I haven't learned about capacitors or inductance at all yet, so thank you for saving that for later. Alright, so I'm a bit confused by the RMS values. This is what my first assignment was on. I don't get what they're trying to say here in terms of, is this line here represents the voltage, whatever it is, root mean squared. Okay. Don't see how, but sure. Is what it is. I don't get what's going on over here as well. So averaged over a cycle. What's this? Is this phi, right? Phi is equal to. I don't get what this is supposed to represent whenever, like, I keep seeing it in K-Shab books. I don't get what that represents at all. But this, anyways, apparently whatever it is equal to 0. Averaged over a cycle. What? Use reactive power, VA, okay, is I times V. And then why is it done RMS? Why would they just okay, so maybe they're gonna mention it here, maybe. To find the power dissipated by the resistor under sinusoidal conditions. To find the power dissipated by the resistor. Okay, basically with a sine wave, we can simply plug the sinusoidal voltage expression into Ohm's power law. Okay. Ohm's power law. This is just the standard law, right? Okay. So nothing. Okay. I was wondering if they're talking about something else. Okay. So P is equal to VI. And what you're saying here is that. Okay. I see what they've done. So they've replaced I with V divided by R. I don't get why though. So to find the power dissipated by the resistor. Okay. So. Power dissipation. Power dissipation. Sine. Okay, so find power. Use Ohm's power law. Or was it a law? Is that what it said? Power law, yeah. This. Okay, so use Ohm's power law. And the sine voltage expression together. Okay, so so this is the voltage expression, right? So what I want to know is why we're replacing I with V over R. Okay, so this looks like what we did here. I think it's exactly the same. I'm not sure why they've done that though. So power over time, okay, is equal to voltage times divided by R. Why are we doing this? I don't get it. I mean, I can see how they've derived the equation. You're just saying that, well, okay, just replace I with V over R, and then that gives you V times V, so you get V squared over R, and then well, P's is part of the peak, the original sine thing. Suddenly now you've ended up squared. Why is sine ended up being squared? 2 pi ft, okay, but why is now sine squared? Did I miss that out in the first part? It wasn't squared in the first part, was it? Yeah, look, it's not squared here. So why have you now squared it here? Okay, because are we doing we're assuming that this is all over R, so okay, no, because the voltage here is squared, and so we're squaring all of this. All right, got it, got it. So I understand how this is derived. I just don't get why it's derived like this. And I find this hard to learn like this. Very hard for me to learn, and oh, just do this. Like, okay, why? Because I'm not gonna remember. Just do this. Oh, okay. I don't even know the point in me writing this down because there's no way this is this for me. For this to stick, I'd have to sit for an hour and a half doing practice problems of this. Anyways, okay, we'll just write it down. Make my I don't know, brain happy. So power over time is equal to voltage. Like to Let me add an extra step from what power is equal to voltage times current, right? And that's equal to voltage times V divided by R. That's equal to V squared divided by R. That's equal to replacing in this. I'm putting this down here. And so then that equals V squared voltage peak divided by R, then times sine squared, and then just the normal 2 pi frequency. Okay, I get that, but I don't get. Yeah, fine, doesn't matter. Basically, so I think we were just trying to use this voltage expression, but why we didn't you just use it? Why didn't we just say P T, so power is equal to, why don't we then just go V P over R times sine 2 pi ft, Why don't we just do that and then all of that times current? I don't know why we didn't do that. Anyways, this is what it is. It is what it is. Expressing voltage, current, and power in an instantaneous fashion is fine. Why is it instantaneous? Let me define that word. Instantaneous. Occurring or done instantly. Express existing or measured at a particular instant. Okay. Expressing voltage and current, and power in instantaneous fashion is fine. I don't understand why it's instantaneous, but okay. Mathematically speaking, however, in order to get a useful result, you need to plug in a specific time, say 1.3 seconds. But how often do you need to know that the voltage, current, or power are? How often do you need to know that the voltage, current, or power are at exactly? Huh? How often do you need to know that the power is at 1.3 seconds? I don't get. Are you trying to say that it's not useful to know what the power is? Okay. Oh, got it. So they're trying to say that, like, for example, why would you want to know, how much power is being used right at this point here? They're saying that, well, you're gonna want to know how much power was used throughout the whole thing, mate, aren't you? And that's what they're saying. These instantaneous values are typically inconvenient for any practical use. Instead, it is more important to come up with a kind of averaging scheme. Got it, got it. Now we're gonna get into RMS. Nice, 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 nice. Okay. So okay. These power equations are not useful. They only provide power for one point on the waveform. So we want to use so okay, these instantaneous values are typically convenient for any practical use. Instead, it is more important to come up with a kind of averaging scheme. We use an averaging scheme to calculate. Starting to make sense to me now. I kind of get now what RMS is. So we're using an averaging scheme to calculate effective power dissipation. I really need to learn about power. Like, that's one thing that I definitely need to learn. So we use an averaging scheme to calculate effective power dissipation without dealing with what? Without dealing sine function. Okay. We use an averaging scheme to calculate effective power dissipation without sine function. Okay. Now you might be clever. I'm not. And consider averaging the sinusoidal voltage or current over a complete cycle to get some meaningful value. You might be clever and consider averaging the sine voltage or current over a complete cycle to get some meaningful value. However, the average turns out to be zero. Ah, yeah. That's true, obviously. Obviously, the positive and negative sides of the waveform just cancel each other out. This may be a bit confusing in terms of power, since the positive going part of the wave still delivers energy, as does the negative going part. Yep. If you ever received a shock from a 120-volt line voltage, you'll be able to attest to that. Mate, I don't think so. Okay. The measurement that is used instead of the average value is the RMS value. Okay, yes. Okay, we're getting somewhere. So we don't use the we don't use the average values since the positive and negative cancel out. So average is 0. Average is 0. Instead, we use root RMS root mean square. So I'm gonna end this video here, and for a particular reason, and it's a bit funny actually. So when I got back, so think about this, right? Yeah, finished my first year, you know, with the whole health situation around the world. Had like 5-6 months off, right, from university. So first day back on a Monday, right? We start our lecture, the first lecture of the second year, and we've never done AC, before, never done capacitors, inductors, nothing, none of that, right? And so, it talks about, talks for like a couple minutes about assessments, and then straight away, probably 2 minutes in, 3 minutes in, he's talking about root mean square values, RMS values, how to calculate the RMS values. And I was like, what is this even English? What does it mean? RMS values, root mean square values. And so look, I think I'm 4 hours now into this book. It's taken me 4 hours to get here. 4 hours. And literally we got here in my lecture, within a few minutes. And there was like, yeah, there was no I was about to use I was gonna use an adult analogy, but no, I doubt any kids will be watching this. But yeah, basically, okay, I'll be quiet. But you know what I mean. There was no build up, so to speak. I'm sure you get what I'm saying. Yeah, cool. So yeah, I want to try and keep this video short. I know I always say that, and it's like an hour long. So I don't know how long this video is. I'm gonna guess it's close to an hour. Hopefully not. But yeah, we'll end this video here, and then in the next video, get started straight from RMS values, which I'm looking forward to because I feel like now I'm going to be able to understand what root mean square values are. So yeah, look forward to this. And yeah, I'll see you guys in the next video. Thanks for watching, and please leave a like and maybe drop a comment. I appreciate it. Thank you.